Alkyne on treatment with H2, palladium, platinum, nickel, platinum oxide. So this reaction is known as hydrogenation. The alkyne group completely reduced and corresponding alkane will be formed. CH3, CH2, CH2, CH3. Similarly, in the second example, the alkyne group completely reduced to corresponding alkane type. The alkyne group converted to alkane type. Similarly, third example, alkyne group will be reduced to corresponding alkane. Similarly, fourth example, the alkyne group reduced to corresponding alkane. Similarly, third example, corresponding alkyne group will be converted to corresponding alkane. So this is the catalytic hydrogenation. Rate of hydrogenation, if I compare, alkyne is more reactive than alkene. And the rate of hydrogenation indirectly proportional to steric factor. And heat of hydrogenation directly proportional to number of pi bonds, indirectly proportional to stability of isomer. And indirectly proportional to stability of alkene. Stability of alkene. When alkyne treated with H2PDBaSO4, sulfur and quinoline, sometimes they don't mention sulfur and quinoline, simply they will give H2PDBaSO4. This catalyst is known as Lindlar catalyst. This catalyst is known as Lindlar catalyst. When alkyne treated with Lindlar catalyst, partial hydrogenation takes place. This alkyne will be reduced partially and corresponding cis alkene will be formed. Corresponding cis alkene will be formed. So ఈ కేసులో మనకి ఓన్లీ సిస్ మాత్రమే ఫామ్ అవుతుంది. Similarly, second example, the alkyne will be reduced to corresponding cis alkene. Corresponding cis alkene. Third example, the alkyne will be reduced to corresponding alkene. ఇక్కడ సిస్ ట్రాన్స్ పాసిబిలిటీ లేదు కాబట్టి వీఆర్ రైటింగ్ సింపుల్ alkene. Fourth example, the alkyne will be reduced to corresponding alkene. Corresponding alkene. Fourth example, the alkyne will be reduced to corresponding cis alkene. It is also cis alkene. So this reaction is partial hydrogenation of alkyne with Lindlar catalyst. When alkyne treated with sodium or potassium or lithium in liquid ammonia, the alkyne will be reduced to corresponding alkene, and here we get only transalkene. Here we get only transalkene. Similarly, in the second example, the alkyne in the presence of sodium or potassium or lithium in liquid ammonia, it will be reduced to corresponding alkyne, and here also we get transalkene. Reduced to corresponding transalkene. Now the important point is, if the alkyne is terminal, in the third and fourth example, the alkyne is terminal, and if the alkyne is terminal, the proton is acidic proton. The proton is acidic proton. Therefore, acid-base reaction takes place. Therefore, acid-base reaction takes place. salt form అవుతుంది and hydrogen will be released in the form of H2. Similarly, fourth example, next fifth example, it is a alkyne. It will be reduced to corresponding trans-alkene. It is a trans-alkene. Therefore, generally internal alkyne when treated with sodium or potassium or lithium in liquid ammonia, it gives trans-alkene. If the alkyne is terminal, this proton is acidic proton. Therefore, acid-base reaction takes place. No reduction. When alkyne treated with H2Ni2b, this catalyst is known as P2 catalyst. H2Ni2b is a P2 catalyst. It is also like Lindlar catalyst. The alkyne will be reduced partially and corresponding cis alkane will be formed. Alkyne will be reduced partially and corresponding cis alkane will be formed. Of course, in the third example, there is no geometrical isomerism. We get simple alkene. Fourth example also, geometric isomerism not possible. We get simple alkene. And fifth example, alkyne will be reduced to corresponding cis alkene. It is also like Lindlar catalyst. When alkyne treated with HBr, so alkyne behave like nucleophile and H plus is electrophile. Therefore, alkyne attract the H plus and corresponding carbocation intermediate will be formed. Stable carbocation intermediate will be formed. It is a vinyl cation. Now it reacts with Br minus and corresponding product will be formed and it is a vinyl bromide. When halogen connected to double bond, it is a vinyl halide. Suppose if I add again HBr, it will form stable C plus it is a stable C plus. Now it again react with Br minus. So Br minus will be attached to corresponding carbon and finally we are getting geminal halide. If two functional groups are connected to same carbon, that is a geminal carbon and therefore it is a geminal dihalide. Therefore, when alkyne treated with HBr 2 times, always we get geminal dihalide. When alkyne treated with 2 moles of HBr, always we get geminal dihalide. Second example, alkyne attract the H plus, stable C plus will be formed. It is a stable C plus because of resonance effect of benzene it reacts with Br minus, and corresponding vinyl bromide is formed. Again, it reacts with another HBr molecule. It reacts with H plus and stable C plus will be formed. Stable C plus will be formed. Now it reacts with the Br minus and finally we get geminal dihalide. Finally we get geminal dihalide. Third example, alkyne react with HBr, H plus and corresponding stable C plus will be formed. Now it reacts with Br minus, corresponding vinyl bromide will be formed. It is a vinyl bromide. Again, it reacts with another molecule of HBr and forms corresponding stable C plus. Now it reacts with Br minus and forms corresponding geminal dihalide. Geminal dihalide. Next example, alkyne treated with HBr. So alkyne attract the H plus and stable C plus will be formed. Now it reacts with Br minus and corresponding vinyl bromide will be formed. Vinyl bromide will be formed. Now it reacts with another molecule of HBr and forms stable C plus. And forms stable C plus. Now it reacts with Br minus and it forms finally the corresponding geminal dibromide. Next example, when alkyne treated with HBr, alkyne attract the H plus, stable C plus will be formed. Now it reacts with Br minus and corresponding vinyl bromide will be formed. If it reacts with another molecule of HBr, alkene react with HBr and corresponding stable C plus will be formed. And the stable C plus react with Br minus and corresponding geminal dibromide will be formed. Geminal dibromide will be formed. Next reagent, HBr peroxide. We can take any peroxy molecule. One of the example, benzoyl peroxide. It is a benzoyl peroxide. When alkyne treated with HBr and peroxide, from this combination, first we get Br radical. Br radical attack on the alkyne and form stable radical. Stable radical. Now it takes hydrogen from HBr, second molecule of HBr, and corresponding vinyl bromide will be formed. Corresponding vinyl bromide will be formed. If second molecule of HBr is added in the presence of peroxide, again from this combination we get Br radical, and because of the steric factor, Br attack at the second carbon. Br attack at the second carbon. That means once halogen is substituted in the same carbon, generally halogen not preferred. Therefore, finally we get CH3, CHBr, CBr radical and CH3. Now it reacts with another molecule of HBr, and this radical takes hydrogen radical, and finally we get corresponding 1,2 dihalo compound. 1,2 dihalo. So 1,2 dihalo position is like vicinal. It is called vicinal dibromide. Vicinal dibromide. Therefore, when alkyne treated with HBr in the presence of peroxide, we get vicinal dibromide. When alkyne reacts with HBr in the presence of peroxide, we get vicinal dibromide. Similarly, next example. When alkyne treated with HBr in the presence of peroxide, from this combination we get Br radical. Of course, it is a free radical addition. So Br radical attack at the corresponding carbon and forms stable free radical. Now it reacts with another molecule of HBr, and the C radical takes hydrogen radical and finally forms corresponding vinyl bromide. And this vinyl bromide again reacts with HBr in the presence of peroxide. So from this combination we get Br radical, and Br radical attack at the other carbon and finally forms corresponding radical. Now it reacts with another molecule of HBr, and finally it gives vicinal dibromide. When alkyne treated with HBr in the presence of peroxide, from this combination we get Br radical, and alkyne react with Br radical. It forms stable radical. React with another molecule of HBr, takes hydrogen radical, and finally it gives vinyl bromide. Now this vinyl bromide can react with another molecule of HBr in the presence of peroxide. From this combination we get Br radical. Br radical attack at the other carbon and it gives corresponding carbon free radical. Now this carbon free radical takes hydrogen from second molecule of HBr, and finally we get vicinal dibromide. When alkyne treated with HBr in the presence of peroxide, from this combination we get Br radical. Br radical attack on alkyne and form stable carbon free radical. Now it reacts with another molecule of HBr, and the C radical takes hydrogen from HBr and it gives corresponding vinyl bromide. Now this vinyl bromide reacts with another molecule of HBr in the presence of peroxide. From this combination we get Br radical, and Br radical attack at the other carbon and form corresponding radical. Now it reacts with another molecule of HBr and finally we get corresponding vicinal dibromide. Corresponding vicinal dibromide. When alkyne treated with HBr in the presence of peroxide, alkyne attract the from this combination we get Br radical. Br radical attack on the alkyne and form corresponding stable radical. Now the stable radical takes hydrogen radical from the second molecule of HBr and finally it gives vinyl bromide. Now this vinyl bromide reacts with another molecule of HBr in the presence of peroxide. From this combination we get Br radical, and Br radical will be connected to other carbon because of the steric factor, and we get corresponding radical, and the radical takes hydrogen from another molecule of HBr and finally we get vicinal dibromide. Finally we get vicinal dibromide. When alkyne treated with HCl or HCl peroxide, in both cases we have to follow electrophilic addition like HBr. We have to follow electrophilic addition like HBr. So we know that the peroxide effect or Karash effect, only observed for HBr. HCl and HI and HF, they do not show Karash effect. So therefore we have to consider simply even the peroxide is present in the case of HCl or HI or HF, we should consider only electrophilic addition. And in the electrophilic addition, alkyne attract the H plus and form stable C plus. Now the stable C plus attract Cl minus and form corresponding vinyl chloride. Now this vinyl chloride reacts with another molecule of HCl. So alkene react with HCl and forms stable C plus. Now it reacts with another Cl minus and finally we get geminal dichloride. Similarly for second example, HCl or HCl peroxide. It follows electrophilic addition and we get stable C plus at this carbon. Therefore, we can write the answer directly like this based on the previous examples. Alkyne treated with HCl or HCl peroxide, it undergo electrophilic addition and at this carbon we get stable C plus. Therefore we get corresponding geminal dichloride. Alkyne treated with HCl or HCl peroxide undergo electrophilic addition. At this carbon we get stable C plus and corresponding geminal dichloride will be formed. Alkyne treated with HCl or HCl peroxide, it undergoes electrophilic addition. Of course here both carbons are same. Finally we get corresponding geminal dichloride. So all these examples are geminal dichlorides. When alkyne treated with HgSO4, H2SO4, water is granted. If they don't mention water, we have to consider water. So in this case, alkyne react with Hg plus 2 and forms corresponding cyclic intermediate. Hg plus 2 తో మనకి cyclic intermediate form అవుతుంది. Now this alkene is not connected to any plus R group. Therefore it react with H2O and H2O react with corresponding stable cation, carbocation, and ring opening takes place. Therefore finally we get corresponding product like this. Now it reacts with another molecule of H2SO4. In place of mercury we get hydrogen. In place of mercury we get hydrogen, and finally we get the product like this. Now it is a enol form. Double bond connected to OH is enol form, and from this enol form we can write the corresponding tautomer like this: CH3, C double bond O, CH2, CH3. So finally we get ketone. Finally we get ketone. Next reaction, alkyne treated with HgSO4 and H2SO4, water is granted. Now alkyne react with Hg plus 2, it forms corresponding cyclic intermediate. Now this 3-membered ring connected to plus R group. Whenever the plus R group is present, ring opening takes place and corresponding carbocation will be formed. Now this carbocation react with H2O and we get finally enol type of compound. Now it react with H2SO4. In place of mercury we should write simply H plus coming from H2SO4. It is enol form, and enol form undergo tautomerization, and finally we should write corresponding ketone. In this case also we are getting ketone. Next example, when alkyne treated with HgSO4, H2SO4, water is granted. So alkyne react with Hg plus 2 and form corresponding 3-membered intermediate, cyclic 3-membered intermediate. Now there is no plus R group. Now it react with H2O directly. H2O attack at secondary carbon, ring opening takes place, and finally we get corresponding enol type of compound. Now it reacts with H2SO4. In place of mercury, we should write H plus coming from the H2SO4, and finally we get enol. Finally we get enol. Enol undergo tautomerization. Enol form undergo tautomerization, and finally we get keto form. Finally we get keto form. Alkyne treated with HgSO4, H2SO4 and water. So alkyne react with Hc plus 2, form cyclic intermediate. In this molecule plus R group is present. Therefore ring opening takes place. Stable C plus will be formed. Now it reacts with H2O molecule and forms corresponding enol type of molecule. Now it reacts with H2SO4. In place of mercury, we should write H plus coming from the H2SO4, and corresponding enol will be formed. Now this enol form undergo tautomerization, and finally we get corresponding ketone. Finally we get corresponding ketone. This compound common name is acetophenone. Acetophenone, and IUPAC is phenylethanone. Phenylethanone. When alkyne treated with HgSO4, H2SO4 and water, alkyne react with Hg plus 2, and corresponding 3-membered ring will be formed. There is no plus R group. Now it reacts with H2O. H2O attack at the secondary carbon. Of course both carbons are same. Finally we get enol type of compound. Now it reacts with H2SO4. In place of mercury, we should write H plus coming from H2SO4, and finally we get the compound like this. It is a enol form. Enol form undergo tautomerization, and finally we get corresponding ketone. Finally we get corresponding ketone. When alkyne treated with B2H6, of course the solvent is THF. More sterically hindered carbon, we have to attach hydrogen. Of course in this case both are same. Less sterically hindered carbon, we have to attach simply boron. So this reaction is hydroboration. This reaction is hydroboration. Finally we get corresponding product like this. Of course it is a syn addition. It is a syn addition. When we add H2O to OH minus, H2O to OH minus, suppose H2O to oxygen is labeled, and this reaction is oxidation. So simply in place of boron, wherever the boron is present, same side we should write OH group, and this OH is coming from peroxide. This OH is coming from peroxide, and it is a enol form. Now it undergo tautomerization, finally we are getting ketone. So this overall reaction is known as hydroboration oxidation. Overall reaction is known as hydroboration oxidation. Alkyne treated with B2H6 and the solvent is THF. In this case, more sterically hindered carbon we have to attach hydrogen, less sterically hindered carbon we have to attach boron. Therefore, we get corresponding product PH, CH double bond C, boron is connected and CH3. It is a hydroboration. Now, if we add H2O2 OH minus, it undergo oxidation. In place of boron, simply we should write OH. Now it undergo tautomerization. Since it is a enol form, finally we get corresponding ketone. When alkyne treated with B2H6 in THF solvent, more sterically hindered carbon will be attached to hydrogen. Boron will be attached to less sterically crowded carbon. Therefore, corresponding hydroboration product is like this. Hydroboration product. Now it reacts with H2O2 and OH minus. It is oxidation. In place of boron, we should write OH group. In place of boron, we should write OH group. Now, since it is an enol form, it undergo tautomerization. Finally, we are getting aldehyde. When alkyne treated with B2H6 in THF solvent, more sterically hindered carbon, hydrogen connected, less sterically hindered carbon, boron should be connected. Therefore, corresponding hydroboration product is like this. Now, if we add H2O2 OH minus, it is called oxidation. In place of boron, simply we should write OH. It is a enol form. Now it undergo tautomerization and finally we are getting corresponding aldehyde. Alkyne treated with B2H6 and a THF. Of course, here both carbons are same. One carbon will be connected to hydrogen, another carbon will be connected to boron. Therefore, corresponding product is like this. After hydroboration, it is a final compound. Now it reacts with H2O2 and OH minus. In place of boron, simply we should write OH group. Now it is an enol form. It undergo tautomerization and finally we are getting corresponding ketone. So not only B2H6, we can also consider dicyamyl borane. So our main requirement is boron should connected to at least one hydrogen. And sometimes we can also use 9BBN. In this case also boron is connected to one hydrogen. So for this kind of reaction, the main requirement is boron should be connected to at least one hydrogen. Then we can expect this kind of reaction. When alkyne treated with Br2CCl4, in this case CCl4 is solvent. So our main reagent is Br2 only. So it undergoes electrophilic addition. Alkyne react with Br plus Br minus will leave and corresponding 3-membered ring will be formed. There is no plus R group. Now it reacts with another molecule of Br minus. Ring opening takes place. Of course, it is an anti-addition. Finally, we get corresponding trans-alkene type compound. Corresponding trans-alkene because of formation of 3-membered ring. Now it reacts with another molecule of Br2. Simply this alkene react with another molecule of Br2 and finally we get tetrabromo compound. Tetrabromo compound. Similarly, second compound, alkyne treated with Br2 in CCl4. CCl4 is a solvent and it undergoes electrophilic addition. Alkyne react with Br plus, Br minus will leave. It forms corresponding 3-membered ring. But here plus R group is present. Therefore, ring opening takes place. And finally, we get corresponding stable C plus. Now the C plus react with Br minus. Br minus can attack from the above the plane, from the below the plane. Both possibilities are there. Therefore, in this case, we get cis and trans compound. In this case, we get cis and trans alkenes. Now it reacts with another molecule of Br2. Now this alkene part react with Br2. Finally, we get tetrabromo. Finally, we get tetrabromo. When alkane treated with Br2 CCl4, so alkane react with Br plus and forms corresponding cyclic intermediate. And there is no plus R group. Now it reacts with another molecule of Br minus. At secondary carbon, ring opening takes place. Finally, we get corresponding trans-alkene. In this case also, we are getting only trans-alkene. Now it reacts with another molecule of Br2 and this alkene part will be added to Br2 and finally we are getting tetrabromo compound. Finally, we are getting tetrabromo compound. When alkyne reacts with Br2, initially cyclic halonium ion, cyclic intermediate will be formed. Cyclic halonium ion or cyclic intermediate will be formed. Because of plus R group, ring opening takes place. Because of plus R group, ring opening takes place and it forms corresponding stable C plus. Now it reacts with Br minus. So Br minus attack on the C plus from the both sides. Therefore, we get both cis and trans alkenes. We get both cis and trans alkenes. Now it reacts with another molecule of Br2. This alkene part reacts with another molecule of Br2. Finally, we get tetrabromo compound. Finally, we get tetrabromo compound. When alkyne treated with Br2CCl4, alkyne react with Br plus and forms cyclic halonium ion. Cyclic halonium ion. And this cyclic halonium ion react with Br minus, anti-addition takes place, and finally we get corresponding trans compound. We get trans compound. We get only trans alkene. Now it reacts with another molecule of Br2, and this alkene part react with Br2. Finally we get corresponding tetrabromo compound. Finally we get tetrabromo compound. So these 5 reactions are halogenation reactions. When alkane treated with bromine water or HOBr, bromine water or HOBr. Of course, bromine water has brown color, reddish brown color solution. Now alkane treated with bromine water or HOBr, it takes electrophile from HOBr and finally it forms corresponding halonium ion, cyclic halonium ion. There is no plus R group. Now it reacts with simply OH minus or H2O simply. So OH minus attack at this carbon, ring opening takes place. So we get enol type of compound. We get enol type of compound. Now this enol type of compound undergo tautomerization. Finally we get corresponding ketone type of compound. Corresponding ketone type of compound. Second molecule, when treated with bromine water or HOBr, bromine water or HOBr, alkane react with Br plus and forms cyclic halonium ion, forms cyclic halonium ion. Because of the plus R group, ring opening takes place. Because of the plus R group, ring opening takes place and stable C plus will be formed. Now it reacts with OH minus or H2O for simplification, and finally we get enol type of compound. And this enol type of compound undergo tautomerization, and finally we get corresponding ketone derivative. When alkane treated with bromine water or HOBr, alkane react with Br plus and forms cyclic halonium ion. Cyclic halonium ion. Now it reacts with OH minus or H2O. OH minus attack at secondary carbon, ring opening takes place. Nucleophile attack at secondary carbon, ring opening takes place. Finally we get enol type of compound. Now this enol type of compound undergo tautomerization, and we get finally corresponding ketone. We get finally corresponding ketone. Alkyne treated with Br2 and H2O or HOBr, alkyne react with halogen and it forms halonium ion. It forms halonium ion. Because of the plus R group, ring opening takes place and forms corresponding stable C plus. And form corresponding stable C plus. Now the stable C plus reacts with OH minus or H2O, and finally we get corresponding enol type of compound. Now this enol type of compound undergo tautomerization and we get finally ketone. When alkyne react with bromine water, it forms cyclic halonium ion. Now it reacts with OH minus or H2O. Anti-addition takes place. We get enol type of compound. Now this enol type of compound undergo tautomerization and finally we get corresponding alpha bromo ketone. So these are the reactions of alkyne with bromine water. So the statement is alkyne decolorizes bromine water. సో దీన్ని మనం టెస్ట్గా వాడచ్చు. సో బ్రోమిన్ వాటర్కి బ్రౌన్ కలర్ ఉంది. సో వన్స్ ఆల్కైన్ యాడ్ చేసిన తర్వాత మనకి బ్రోమిన్ వాటర్ అనేది కలర్ లూజ్ అవుతుంది. ఎందుకు లూజ్ అవుతుంది? బ్రోమిన్ వాటర్తో రియాక్ట్ అవటం వల్ల మనకి ఏదైతే సొల్యూషన్ వస్తుందో అది కలర్లెస్ అవుతుంది కాబట్టి. దేర్ఫోర్ ఆల్కైన్ డీకలరైజెస్ బ్రోమిన్ వాటర్. When alkyne treated with cold alkaline KMnO4, it is also known as Bayer's reagent. So in this case, the alkyne connected two carbons will be oxidized to corresponding diketo molecule. Similarly, second example, the internal alkyne treated with Bayer's reagent, the final compound is diketo compound. And it is a terminal alkyne. So in the case of terminal alkyne, we will get corresponding compound like this. But aldehyde again oxidizes, it undergoes oxidation, and finally the corresponding property is CH3COCOOH. It is for terminal alkynes. Similarly, next compound, alkyne treated with Bayer's reagent, corresponding answer, initially we will get corresponding 1,2-dicarbonyl, but it is a aldehyde, undergo oxidation, and finally we get corresponding alpha keto acid. When alkyne treated with Bayer's reagent, it is an internal alkyne, we get simply diketo. In all these molecules, we get brown PPT of MnO2. KMnO4 will be converted to brown PPT. So KMnO4 has purple color. After the reaction, brown PPT is forming. So this reaction also can be used for identifying the unsaturation in the hydrocarbon. So alkene or alkyne, when we add Bayer's reagent, brown PPT will form. It indicates the presence of saturation in the compound, unsaturation in the compound, and sometimes we can use a statement according to, in some questions they give the statement like alkene or alkyne. Decolorize Bayer's reagent. Decolorize Bayer's reagent. Decolorize Bayer's reagent. So decolorize means here color changing. When alkyne treated with KMnO4 heat, hot KMnO4, sometimes they will give hot KMnO4. So we have to break the alkyne bond, and finally we should write corresponding acids CH3COOH and CH3COOH. Second example, when alkyne treated with KMnO4 heat or hot KMnO4, so we have to break the triple bond here, and finally we get corresponding benzoic acid and acetic acid. When propane treated with KMnO4, so we have to break the triple bond, corresponding answer CH3COOH and formic acid, and we know that formic acid undergoes oxidation with KMnO4 in the presence of KMnO4, and finally CO2 will be formed. When alkyne treated with KMnO4 heat, we have to break the triple bond, and the corresponding answer is benzoic acid and formic acid, and we know that formic acid undergo further oxidation, and finally CO2 will be formed. When alkyne treated with KMnO4 or hot KMnO4, it is an internal alkyne, therefore corresponding answer dicarboxylic acid. So this is the reaction with hot KMnO4. When alkyne treated with ozone followed by zinc H2O or zinc acetic acid, dimethyl sulfide or triphenylphosphine. So this is called reductive ozonolysis. This reaction is reductive ozonolysis. So all these examples are reductive ozonolysis. In the reductive ozonolysis, wherever the triple bond is present, so simply we should write corresponding answer CH3 C double bond O, C double bond O, CH3. So both keto carbons will undergo oxidation, and finally dicarbonyl compound will be formed. The second example also, the alkyne connected carbons undergo oxidation, and corresponding dicarbonyl compound will be formed. Even for terminal alkynes also, the corresponding answer is CH3 C double bond O, CH double bond O, dicarbonyl compound. Next, terminal alkyne, this compound also undergo oxidation and corresponding dicarbonyl compound. Similarly, cyclooctane also undergo oxidation, and finally corresponding dicarbonyl compound will be formed. Alkyne, when treated with ozone and H2O and H2O2, H2O or H2O2, this is called oxidative ozonolysis. This is called oxidative ozonolysis. In the oxidative ozonolysis, we have to break the triple bond, and finally we should write corresponding acids CH3COOH, CH3COOH. Next compound, so we have to break the triple bond, and finally we should write benzoic acid and acetic acid. We have to break the triple bond, we should write acetic acid and formic acid. We should break the triple bond, benzoic acid and formic acid. We should break the triple bond, corresponding dicarboxylic acid. Corresponding dicarboxylic acid. When alkyne treated with NaNH2 followed by RX, So with NaNH2, internal alkyne, no reaction. No reaction. Now next one, alkyne treated with NaNH2, internal alkyne, NaNH2 is a base, no reaction. But when terminal alkyne treated with NaNH2, this is acidic proton, NH2 minus is base, therefore acid base reaction takes place. NH2 minus take the proton and ammonia will be formed. If it is treated with RX, now we expect SN2 type of reaction, and corresponding answer is CH3, C triple bond C, R. When the terminal alkyne treated with NaNH2, terminal alkyne is acidic, NH2 minus is base, so acid base reaction takes place and salt will be formed. And this salt acts as nucleophile. When it is treated with RX, nucleophilic substitution takes place through SN2 mechanism, and finally the compound is PHC triple bond C, R. Suppose internal alkyne treated with NaNH2, internal alkyne treated with NaNH2, there is no reaction. There is no reaction. When alkyne treated with Tollens reagent, AgNO3 NH4OH, otherwise AgNH32 plus, otherwise simply sometimes they will mention ammonical silver nitrate. Ammonical silver nitrate. So this is a Tollens reagent. So Tollens reagent react only with terminal alkyne. If it is internal alkyne, there is no reaction. Internal alkyne, there is no reaction. Internal alkyne, there is no reaction. So internal alkyne to Tollens reagent react kaadu. But if the alkyne is terminal, so this proton is acidic. This proton is acidic. Therefore, in the presence of ammonia, acid base reaction takes place, and finally it gives the corresponding salt CH3, C triple bond C minus and Ag plus. So it is a white PPT. It is a white PPT. Similarly, in the fourth example also, corresponding salt PH3, C triple bond C, Ag. It is also white PPT. It is also white PPT. So this can be used for testing of terminal alkyne. Testing of terminal alkyne. The given, if you want to know the given alkyne is internal or terminal, simply perform the Tollens reagent test. If we add Tollens reagent, if white PPT is formed, then the alkyne is terminal. If white PPT not formed, then alkyne is internal alkyne. When alkyne treated with CuCl and NH4OH, so it is also in the presence of basic medium. Internal alkyne, there is no reaction. To the alkyne, if we are adding CuCl and NH4OH, if it is internal alkyne, there is no reaction. When the terminal alkyne treated with CuCl and NH4OH, and this is acidic carbon, this carbon is acidic, therefore acid base reaction takes place and corresponding copper salt will be formed. And this copper salt is red PPT. This copper salt is red PPT. The terminal alkyne treated with CuCl and NH4OH, CuCl and NH4OH, acid base reaction takes place and finally copper salt will be formed. And this copper salt is red PPT. Red PPT. Internal alkyne treated with CuCl and NH4OH, there is no reaction. Internal alkyne treated with CuCl and NH4OH, there is no reaction. So again, it is also test for terminal alkyne. An alkyne treated with internal alkyne treated with sodium, no reaction. Sodium hydroxide, no reaction. Sodium bicarbonate, no reaction. Grignard reagent, no reaction. Internal alkyne do not react with the sodium, sodium hydroxide, sodium bicarbonate and Grignard reagent. Similarly, next example, internal alkyne, sodium, no reaction. Sodium hydroxide, no reaction. Sodium bicarbonate, no reaction. Grignard reagent also, no reaction. When the terminal alkyne reacts with the sodium, there is acid-base reaction CH3, C triple bond C minus Na plus half H2 gas. The acidic proton will be converted into H2 gas. The terminal alkyne NaOH, no reaction. Terminal alkyne sodium bicarbonate, no reaction. But Grignard reagent acid-base reaction takes place. CH3, C triple bond C minus MgX plus and corresponding alkane. Terminal alkyne, it is acidic proton. Sodium acid base reaction takes place and corresponding salt will be formed, and sodium bicarbonate not enough base to react. Sodium bicarbonate also not enough base to react, and Grignard reagent acid base reaction takes place. Grignard reagent acid base reaction takes place. Grignard reagent acid base reaction takes place. Internal alkyne, sodium, no reaction. Sodium hydroxide, no reaction. Sodium bicarbonate, no reaction. Grignard reagent, no reaction. When alkyne treated with red hot iron tube, it undergo trimerization. Alkyne, it undergo trimerization like this, and we get the corresponding properties: benzene and 6 methyl groups. It is cyclic polymerization of alkyne. Similarly, next compound, alkyne, PHCH3, PHCH3, PHCH3. Now it undergo trimerization like this, and finally we get corresponding compound benzene, pH. Like this we will get. Suppose propane undergo trimerization. And we get the final compound like this: benzene, methyl, methyl, methyl. It is also called mesitylene. Similarly, phenylacetylene also undergo trimerization, and we will get corresponding triphenyl compound. Similarly, cyclooctane also undergo trimerization, and we get finally corresponding compound. So here we should write 8-membered ring. 8-membered ring. 8-membered ring. 8-membered ring. So this is a cyclic polymerization of alkyne. One of the important reaction is acetylene. When it undergo trimerization, it gives benzene. Acetylene undergo trimerization, finally it gives benzene. Memory based reaction. Suppose the internal alkyne treated with NaNH2, it is also called sodamide, NaNH2, and strong heating. Internal alkyne, finally it will be converted into terminal alkyne. Internal alkyne will be converted into terminal alkyne. Finally it gives corresponding salt. Suppose that terminal alkyne treated with alcoholic KOH and the solvent is paraffin oil and we are heating. If the alkyne is internal, if the alkyne is terminal, if the alkyne is terminal, the alkyne is terminal, the terminal alkyne will be converted into internal alkyne. Internal NaNH2, terminal alcoholic KOH, internal. So these two are memory based reactions. So depends on the question, you should understand and you should give the answer.